All right, this is Math 1400, Section 2.3. If you are watching this and you haven't already watched the lessons for Section 2.4, I actually would like you to go back and watch 2.4 first. I'm doing these two sections out of order. So, assuming you have seen the lessons for 2.4, then let's get into it. So Section 2.3 really digs into how we can evaluate limits of functions more analytically, like more rigorously, as opposed to just doing things like estimating the limit graphically or numerically. First of all, what we learned from Section 2.4 was that if functions are continuous, then their limits equal the function value, and that gives us something that this section refers to as direct substitution as a strategy for finding limits. And it is just, if f of x is continuous at c, then the limit as x approaches c of f of x can be found by just substituting in c to the function and calculating f of c, right? I know that technically limits don't depend on the function value. They depend on what the function is doing as you approach the value. But in this case, with continuous functions, they're equal. Remember, this works for any function. This is really useful for any function that's continuous on its entire domain, like polynomials, rational functions, radical functions, all the basic trigonometric functions, as well as exponential and logarithmic functions. So all those basic functions that you learned about in pre-calculus, we can apply this to. If you start combining them together in weird ways, then it might get a bit hairy. But we do have rules for that too. So what I want to do next is back up from direct substitution and let's establish some really basic limits. And then we're going to build up some limit properties that we can apply to prove limits. So the first really basic limit will be the limit of the most basic function we can think of, which would be a constant function. Let's say you want to know the limit as x approaches some number, doesn't matter what number, call it c because it's could be anything, of some constant function. We'll call that one b. What is that going to be equal to? Well, let's draw a little picture. The function's constant at height b, right? And we're talking about what happens as x approaches c. Well, oops, I'm sorry, I wrote x. I meant to write c. If x is approaching c, either from the right or the left, what's happening? The point's coming along this line, staying in exactly the same height and approaching this point right here, right? Well, it looks to me like that point is at height c. Sorry, at height b. Yeah, because it's not going anywhere, right? It's always at height b. So what's it approaching? B. So that's the most basic limit we can have. The second most basic limit would be, what's the limit as x approaches c of the function x? This one's great. I love this one because it's just asking, hey, as x approaches c, what is x approaching? It's c, right? It's a tautology. It's like you're saying, hey, if A, then how about A? Yeah, check it out, A. So here's the explanation, the graphical explanation. Here's our line y equals x. We're asking what happens as the x values are approaching c right here. Well, the point on the curve that we'd be approaching would be also at height c, since y equals x. So the y coordinates are approaching c as well. So that's those are our two super basic building blocks. So now let's jump in and do some properties. These are going to be like rules for figuring out limits, very sort of abstract rules for figuring out limits. So in order to go through these, we've got to make some assumptions. First, let's just suppose that the limit as x approaches c of the function f of x exists and equals L, and the limit as x approaches c of this function g of x exists, and that one's going to equal k. Oops. we have these two functions, f and g, and their limits at c both exist, and they're equal to L and K respectively. So, first property. If you have the limit of some constant multiple of a function, so we're going to use b to represent a constant again. If you have a constant multiple of a function, then the limit of that is going to be the constant multiple of the limit of that function. Which in this case, because the limit of f of x was said to be L, this would be BL. This property is called the constant multiple rule for limits. Second, if you look at the limit of either sum or difference, so it's plus or minus, one or the other, not both, of the two functions f and g, then we can calculate the limit of that sum or difference by just doing the sum or difference of the limits of the two functions. That would be like L plus or minus K. So that's called the sum or difference rule for limits. In a way, it's like the limit operator that you're applying to this function is sort of distributing over the addition or subtraction. In a sense, it looks a little like distributing, right? The next one is similar, except this time we're dealing with products. F of x times g of x. And again, the limit appears to distribute over the multiplication, because this is the same as taking the limit of f and taking the limit of g, and then multiplying them together. So this is going to be L times K. So far, and that's, by the way, called the product rule for limits. So far, that's pretty straightforward. The last one, as you can imagine, is going to deal with division. We've got constant multiples, we've got adding and subtracting functions, we've got multiplying functions. What about dividing functions? Yes, it's going to work exactly like you expect with one extra stipulation. Okay, this is going to be the limit of f divided by the limit of g, provided, which is going to equal, I guess we'll say that's going to equal L over K, provided K is not 0. So that one works only if the limit as x approaches c of g of x, that K value there, isn't 0, obviously, because we can't divide by 0. So we've got that. And then two more here. One is if you're taking the limit of some function that is then raised to a power, that's going to equal the limit of the function, raised to the power as well. I got to wrap this up because my son just woke up from a nap, but there's another one where instead of a power, it's a radical, but actually we can wrap those all together into a single rule if we say that n is allowed to be any rational number, either a integer or a fraction, and that would encompass all powers like squared, cubed, to the fourth, etc., or things like the nth root. Negative numbers like to the power -1 or to the power -2, those should work too. So I gotta go, but see you in the next video.